Welcome. This video is CCBYNC. Welcome back. For this lesson, we're going to go through some of the reasons why we would even consider using instead of degrees. We're going to start with arc length. Arc length is when we have a circle and we have what's called a central angle, meaning from the center, we form an angle with the radius r. The angle is theta. Now, theta must be in radians. Central angle of theta radians. If it's not in radians, we're going to have to convert it. And the formula we end up with is this one here. S, which is the arc length, is equal to r times theta. Once again, theta needs to be in radians. So for our first example, we have that a circle has a radius of 13 feet. And we want to find the radian measure of the central angle theta that intercepts an arc length of 16 feet. I want to emphasize once again, when we're talking about arc length, we're talking about the distance from here to here, based on r, based on theta. So we have a radius of 13, and we have an arc length already written out for us of 16. And they're both in units of feet, which is nice. We don't have to do any converting. So if I use the formula S equals r times theta, and we're looking for theta, this means 16 is equal to 13 times our unknown theta. This means theta is going to be 16 over 13. And they want us to round to the nearest tenth of a radian. 16 divided by 13. So that's 1.2 radians. 1.2 radians. For our second example, we have a circle of radius 4 inches. You don't have to draw the circle every time, but sometimes it's a good visual. Find the length S for the arc intercepted by a central angle of 66. Now notice we're in degrees, and round your answer to the nearest tenth. So we have r is 4. Theta we have is 66 degrees, but we're going to have to convert that into radians. So our overall arc length, which is r times theta, is now going to be 4 times 66 times pi over 180. So we have 4 times 66 times pi divided by 180. And in case you missed it, the pi button on my calculator is above the caret. So we're getting about 4.6, and this is going to be in inches. Next up, find the distance that the Earth travels in one day in its path around the sun. Assume that a year is 365 days. In real life, it's not. It's a little different than that. And that the path of the Earth is around the sun is a circle, which again, it's not. It's elliptical, but we're going to assume that it is, and has a radius of 93 million miles. And we're going to run nearest tenth, which is 100,000. I'll get to that in a second. All right, so first thing I need to do is figure out what the angle is in one day. We know that one day is 365, 1 year. Year is 365 days, in which the Earth goes around the sun in a full circle, which we know is 2 pi radians. So if I divide both sides by 365, that will tell us that we have one day is 2 pi over 365 radians. So now we have our theta. This is our theta. We have r, which I'm just going to use the 93, and we'll convert it to million in a moment here. So how far does the Earth go? Let's see. This is r times theta. R in this case is the 93 million times our angle, which is 2 pi over 365. Let's see what we get. 93 times 2 times pi divided by 365. So it looks like the Earth moves about 1.6 million miles in one day. That's amazing to think about. So from noon one day to noon the next day, we will have traveled in space 1.6 million miles. Amazing. Next up, that was arc length. We're now going to do sector area. Sector area is slightly different than arc length in the sense of, instead of looking for the distance we're going around, we're now looking for the area that it slices out of a circle. And the formula that we're going to be using is right here. A equals 1/2 theta r squared. Once again, theta must be in radians, A circle has a radius of 4 millimeters. A sector of the circle of the central angle is 140 degrees. We'll have to convert that. Find the sector area and round to the nearest tenth. So we have A is equal to, here's our theta. Let's convert that over here. Theta is 140 times pi over 180. We can reduce that actually to 7 pi over 9. So our area is going to be 1/2 theta, which is 7 pi over 9 times r squared. So that's 4 squared. So 1/2 times 7 times pi. And I'm going to say times 16. I went ahead and squared that 4. Then divided by 9. Give me about 19.5 square. We are in millimeters. Once again, those of you watching this video, you should have a calculator and be doing these yourself. Next up, the area of a sector of a circle with a central angle of 0.8 radians, they've already given it to us in radians, which is nice, is 21 square centimeters. So in this case, they've given us the area, and they want us to find the radius. So again, in this case, we have area is equal to 1/2 theta r squared. And in this case, we're looking for give us A, which is 21. They give us theta, which is 0.8. Then we have r squared. Half of 0.8, it's over here, 21 equals 0.4 r squared. And dividing out the 0.4, we get 21 divided by 0.4, 52.5. Not done. Now I have to take the square root of that. So r, we're going to say r is always positive, so we don't need to do the plus or minus there. So 52.5, square root of that. Give us about 7 point, and they want us to round to the nearest tenth, 7.2, and the unit on that is going to be centimeters. So that's sector area. Now we're to the last two parts. We have angular and linear velocity. So this is velocity means speed for our purposes right now. When we get to vectors, we'll talk about the difference between speed and velocity. And angular velocity, meaning we're measuring the angle, how fast it's moving. And here's the formula that we use. This is a Greek letter omega. It's a lowercase omega. And omega is equal to theta, which once again is in radians, divided by time. Now, linear velocity, now the difference between angular and linear velocity, angular is measuring how quickly the angle is changing, versus linear velocity is if I'm on this thing, how far am I walking? Or how fast am I walking, pardon me. And that's given by V equals S over T, where once again, S is R theta. And there's variations to this. We could say that V is also equal to omega times R is another way, because you can see the S is going to be R theta, but you can see theta over T, which is the omega times the R. So there's different variations for it. All right, example 6, a Ferris wheel at a carnival has a diameter of 74 feet. Now, a diameter of 74 feet means when we chop that in half, yep, 74 divided by 2 gives us 37. So I want us to keep in mind that R is 37 feet for this example. A diameter is all the way across versus radius, which is from the center out. And it turns out a rate of 2 revolutions per minute, and they want the angular speed. This actually is sort of an angular speed, but what we're going to have to do is take the 2 revolutions per minute and we are going to have to change it to radians. Now, 1 revolution is the same thing as 2 pi radians, or 360 degrees if we wanted to use degrees for some reason. So when I convert this, just do that. This is a trick I learned in college, where I set the units so that they cancel out, and what I'm left with are radians per minute, which is exactly what they're looking for. So it looks like we are at 4 pi. This is radians per minute, and this is our omega. All right, part B. We are just going to multiply that, our omega, times R. So our linear velocity is, I wrote the extra form, there it is. Velocity, another way of writing it is omega times R. So I'm going to take the 4 pi, which is our omega, times R, which we figured out was 37 feet. And that's going to give us 4 times pi times 37. There we are. So 464.96. Oh, they want nearest whole numbers, so they can do that. This is 465. And this is going to be in feet per minute. There we are. And I'm noticing for omega, I didn't actually get a rounded value for that. So that's 4 times pi. 4 times pi. And rounding that off, that's going to be about 13 radians per minute. All right. Example 7. The restaurant at the top of a very tall building in Seattle rotates at 1.02 revolutions every hour. Luo Li sits 22.1 meters from the center of the restaurant near a window. Now that's going to be our radius, our R, when we get to it. And we're going to round our answers to 2 decimal places. Part A. Through how many radians does she turn in 115 minutes? So I need to, and I'm going to notice that we have 1.02 revolutions. This is per hour. So I need to convert both the revolutions into radians and the hours into minutes. So 1 revolution is 2 pi radians. And I know that 1 hour is 60 minutes. I'm going to use that trick again, where the hours reduce out and the revolutions reduce out, and I'm left with radians over minutes. So this is going to be 1.02 times 2 pi, 2 times pi, divided by 60. So this is our theta, our omega, pardon me. But they don't want to know per minute. This is radians per minute. They want to know after 115 minutes. So I'm going to take that number and multiply it times 115. That's a 0. And you'll notice the minutes cancel. So I'm going to take that number times 115. Here we have it. This is going to be 12.28. It says 2 decimal places, radians. Part B, all we're going to have to do for this one, and this is theta now that we've just figured out. Part B is going to be how far, so that's S equals R times theta, that's arc length. R in this case is 22.1 times my theta, 12.28. That is going to give us times 22.1, 271.47, and that is going to be in meters. Not too bad. I hope that helped.